Hello and welcome back to Realms Explorer. Today, we explore the one process that can send a black hole back to meet its maker. Hawking radiation. So, let's get into it, shall we? What is Hawking radiation exactly, and what does it have to do with black holes and their death? Well, in two words, vacuum fluctuations and zero-point energy. These are at the very heart of black hole behavior. Let's first find out what normal vacuum is like. Vacuum is by no means just an empty space. Empty space still has the quantum fields because they're continuous, all-pervasive fields. But they are at their baseline value, which is zero, except for the Higgs field, which has a positive baseline value. Now, these fields are not always just static. Virtual particles often pop up due to fluctuations in these fields, and always do so in matter and antimatter pairs. You know, to conserve energy, because there was zero energy at that point to begin with. And, being matter-antimatter pairs, they usually annihilate each other and return the energy back to the field. And these pairs exist only for a really teensy bit of time. This is how normal vacuum works. Next, we will see how this changes in a black hole. Now, let's see what happens to these vacuum fluctuations inside a black hole, that is, inside the event horizon. For some reason, these vacuum fluctuations occur at an increased frequency. And not just that, as soon as they are created, one of the particles gets separated and blasted off as Hawking radiation. That means that the other particle cannot combine with its counterpart. Sadly, this means the field which had earlier due to fluctuation given rise to the two particles cannot now return to its baseline value. Unless the left-out particle combines with some other particle, which is its counterpart, so part of the matter which is already inside the black hole is used up to return the fields back to their baseline values. Without new mass falling into the black hole would soon evaporate, as there would be no mass left inside it. The vacuum fluctuations inside the event horizon act as an engine, driving the black hole into oblivion, and Hawking radiation is the exhaust from that engine. What if I said everything we've talked about Hawking radiation until now is just a child's analogy? Indeed, it is so, and I'm sorry for misleading everyone, but that analogy forms the basis to understand this phenomenon in more detail. First of all, Hawking radiation is a theoretical prediction born out of quantum mechanics and general relativity. Partial experimental proof does exist though, and the theory is very solid. This is mostly due to our current inability to actually make good observations of a black hole. The problem is that astrophysical black holes are extremely cold. Understandably so, because they don't allow radiation to flow outwards. A black hole, the mass of the Sun, would emit Hawking radiation at a temperature of only about 6 × 10⁻⁻8 Kelvin. That is vastly colder than the cosmic microwave background, so any Hawking radiation would be drowned out by surrounding radiation. This makes it hard to detect or confirm. What the actual theory says is this. Near the event horizon, quantum fields fluctuate, and mathematically this leads distant observers to see a thermal spectrum of particles escaping. This is called the Unruh effect. It's just relativity adding its touch of magic to quantum fields. We will see how this adds up in a bit, so bear with me for a few minutes. One more interesting prediction of the theory is that the math says that the smaller the black hole, the more the radiation. So tiny primordial black holes, if they exist, could potentially evaporate violently and be observable. Laboratory analog Hawking radiation has been observed in systems like Bose-Einstein condensates and optical media. These are not real black holes, but they reproduce similar horizon mathematics. In a bit, we will explore how exactly these quantum field eccentricities result in Hawking radiation. As I said earlier, that the particle-antiparticle pair at the horizon story is actually a simplified analogy. It's useful for intuition, but it is not literally the fundamental derivation of Hawking radiation. The real calculation comes from quantum fields in curved spacetime. But the pair picture tries to capture the basic energy bookkeeping in a visual way. Before we dig into these phenomena, I'd like to make a few things about quantum field theory clear. 1. These fields are not something just mathematical that we sort of invented, they pop out by themselves when we take into account the symmetries that naturally exist in our universe. 2. We define a particle as an excitation or a vibration in these fields. 3. These fields are all superimposed upon one another, and in the end, built upon the underlying space-time fabric. 4. There's something called a mode, or in better terms, a quantum mode. It's nothing but a possibility, or in other words, a degree of freedom. Essentially, these are solutions to the field that say which type of vibration is possible and what can happen to the vibration as time progresses, forwards or backwards. All this means is that they're blueprints which a future vibration, in other words, a particle can follow and exist as. 5. Most importantly, everything in our universe is relative. That's what relativity says. The same is true for these quantum fields. The baseline value for the field, the vibrations or the particles, everything is relative. This is the Unruh effect, that is, the relativity of quantum fields. This happens because, when you define a vibration, how do you do it? You define it in terms of frequency, etc. But when you do this, you're using time. And time is relative. Usually in flat spacetime or at lower speeds, there's not much of a difference, but when the gravity is too high, or the speed is too high, these changes are much more noticeable. What this means is that, since time is relative, both the modes, the particles, and the field itself, which use time in their definitions, become relative. Which means, someone who is far away in a different inertial frame can observe radiation or particles, when someone else in a different inertial frame sees nothing but vacuum. This is not fake, but real actual detectable change in the field. If you take a detector and move at high enough speeds, your detector will detect radiation, even when someone stationary says there's nothing there at all. This is the Unruh effect, and in part explains Hawking radiation. We will see how next. Coming to Hawking radiation, this is how our most modern theories explain it. As we've seen earlier, modes are in the most basic sense, possibilities of what kinds of particles or waves can exist, and what kind of trajectories and futures they can have. At the horizon of a black hole, the structure of the modes is affected. Since something inside a black hole cannot communicate with something outside, this means that the inwards modes are completely cut off from the outwards modes in a causal way. That is, a solution to the field that says a particle can cross the horizon or communicate with a particle on the other side doesn't exist. But we also know there's something called entanglement, and when particle pairs are created, or even the modes themselves are entangled, this separation added on creates many mathematical abnormalities. Now, coming back to the Unruh effect. Since we faraway observers from Earth are in a relatively flat spacetime and moving away from the black hole at high speeds, the outward modes and the quantum field itself that we observe near the highly curved spacetime of the black hole is different. The relative difference in our inertial frames means that the way we define these modes and particles is different. Meaning, one person can see a particle where another just sees empty space. Hence, we observe a constant thermal radiation, which is the Hawking radiation. The outward modes, that is the possibilities for particle trajectories, that exist near the event horizon, appear to us as if being realized. In other words, as if generating detectable particles all the time. But to an observer right at the edge of the black hole, it would seem like the space is no different from vacuum somewhere else. Speaking in a coarse way, it changes the energy these fields or vibrations in them exhibit that we can perceive. This is to be expected, as the frequency etc. are defined based on time, and time is relative. These are not fake though, but real detectable particles, and it is a result of relativity. It is as real as your hands and feet. This is the most modern interpretation of Hawking radiation that I can provide. Thank you for listening, and hope you enjoyed that journey into Hawking radiation. On a side note, sometimes I think and feel as if I have explained something very well, only to realize it was nearly not as transparent. So, please ask any questions, no matter how small they seem, that you are left with after listening to this, in the comments below.